Welcome, my dear students, on a new lecture of functional analysis. In the previous lecture, we have discussed about the projection map, which maps a Hilbert space H onto a subspace P maps H onto some subspace Y. And we have discussed some of its properties. One of the main properties of the map was P maps Y perpendicular onto set 0. So, the elements x element of h for which p of x is equal to 0 are those elements which belongs to y perpendicular. So the elements with which p of x is equal to 0 is actually the null space of p. So which means that y perpendicular is the null space of the projection map p which maps h onto y. So we can formally state that as a theorem. So it states that the orthogonal complement y perpendicular of a closed subspace y of a Hilbert space H is the null space n of p of the orthogonal projection p from S to y. So നമ്മൾ p എന്ന് പറഞ്ഞ ഓർത്തോഗണൽ പ്രൊജക്ഷൻ എച്ചിൽ നിന്ന് വൈയിലേക്ക് ഡിഫൈൻ ചെയ്യുകയാണെങ്കിൽ ആ വൈയുടെ പെർപെൻഡിക്കുലർ സ്പേസ് ആയിരിക്കും ആ പ്രൊജക്ഷൻ്റെ നൾ സ്പേസ്. കാരണം വൈയുടെ പെർപെൻഡിക്കുലർ സ്പേസിൻ്റെ അകത്തെ എല്ലാ എലമെൻസിനെയും പി സീറോ എലമെൻറ്റിലേക്കാണ് മാപ്പ് ചെയ്യുന്നത്. സോ ദിസ് ഈസ് ദ one of the important result regarding the projection of a projection function which is defined on a Hilbert space. Now moving on, using this we can define a new terminology called annihilator. So annihilator means the collection of all elements on a inner product space such that the elements are actually perpendicular to a set. So we have defined that if you define a convex subset, if you have a space X and a convex subset X, there exists at least one element which is actually perpendicular to M. Okay, we have already defined that. Now there may be lot of elements which is actually perpendicular to the set. The collection of all such elements is called the annihilator of M. Now formally defined as, so the annihilator M perp of a set M which is a non-empty set in an inner product space X is the set. M perp is set of all x element of the inner product space X such that X is perpendicular to M. That is, an element X is an element in N perp if inner product xv is equal to 0 for all v element of M. സോ അനിഹിലേറ്റർ എന്നതുകൊണ്ട് ഉദ്ദേശിക്കുന്നത് ഒരു സെറ്റുമായിട്ട് പെർപെൻഡിക്കുലറായിട്ട് വരുന്ന സെറ്റിൻ്റെ എല്ലാ എലമെൻസുമായിട്ടും പെർപെൻഡിക്കുലറായിട്ട് വരുന്ന കളക്ഷൻ ഓഫ് എലമെൻസിനെയാണ് നമ്മൾ അനിഹിലേറ്റർ എന്ന് ഡിഫൈൻ ചെയ്യുന്നത്. നൗ ദിസ് അനിഹിലേറ്റർ ഹാസ് a certain set of properties. The first property is actually it's a vector space. Okay, so the first property regarding annihilator is M perpendicular is a vector space. So in order to prove that it's a vector space, we have to take two elements. Let x comma y element of M perpendicular. Then we have to prove that alpha x plus beta y is again an element of M perpendicular. Okay, since x and y element of M perp inner product xv is equal to 0 and inner product yv equal to 0 for all v element of M. Now In order to prove that alpha x plus beta y element of M perp, we only have to look inner product alpha x plus beta y v, which by definition of inner product is actually alpha times inner product xv plus beta times inner product yv. Inner product xv is actually equal to 0, so alpha times 0 is 0. Inner product yv is actually 0, so beta times 0 is 0. So total answer will be 0. So which means that for all v belongs to M, inner product of alpha v plus beta y is orthogonal to v. So which means that alpha x plus beta y element of M perpendicular. So whenever x and y element of M perpendicular, its linear combination alpha x plus beta y is again an element of M perpendicular. So which means that M perpendicular is a vector space. The second property of M perpendicular is M perpendicular is a closed subspace. Closed subspace. That's the second property. So now, in order to prove this, we have to prove that M perpendicular closure should be equal to M perpendicular. Now we already know that for any space, M perpendicular is actually a subset of M perpendicular closure. Now the only thing which remains to prove is we have to prove that M perpendicular closure is a subset of M perpendicular. For that, consider an element y element of M perpendicular closure. Then, by definition, there exists a sequence yn which belongs to M perpendicular such that yn converges to y. Now we have to prove that this y belongs to M perpendicular. Okay, so yn belongs to M perpendicular means inner product yn v should be equal to 0 for all v element of M. Okay, now in order to prove that y is an element of M perpendicular, we have to prove that inner product yv is equal to 0 for all v. So take inner product yv, which by definition y is actually limit yn v, which should be equal to, if you take limit outside, limit yn v. Now yn v is actually always equal to 0. So this is actually equal to limit n tends to infinity 0, which is actually equal to 0. So which means that inner product yv is also 0. So which means that y is an element of M perpendicular. That is, y is an element of M perpendicular closure implies y is an element of M perpendicular, which implies M perpendicular closure is a subset of M perpendicular. Okay. Now, which implies both of them together, we can state that M perpendicular closure should be equal to M perpendicular. Okay. So that's the idea. So it's a closed subspace. Now we have another property which states that we can define M perpendicular the whole perpendicular. So which is the collection of all elements which is actually perpendicular to M perpendicular. Now which is actually usually denoted as M perpendicular perpendicular, and if M is an arbitrary space or subset of a space, then M is always subset of M perpendicular perpendicular. This is another property. For that, consider let x element of M. Then inner product xy equal to 0 for all y element of M perpendicular. Okay. Now this implies x is actually perpendicular to M perpendicular, because inner product xy is equal to 0 for all y which is an orthogonal complement of M, or y belongs to M perpendicular. M perpendicular consists of all the elements which are actually perpendicular to the elements of M. Now x is an element which is perpendicular to M perpendicular. M perpendicular perpendicular consists of all those elements which are actually perpendicular to M perpendicular. So this implies x is an element of M perpendicular perpendicular. That is, for every x element of M, x is an element of M perpendicular perpendicular. That is, M is a subset of M perpendicular perpendicular. That's the idea. Okay. So thus we have proved some elementary properties of the annihilator. Annihilator means the collection of all elements which are perpendicular to a particular elements of a set in general, all the elements of a set. And we have already established that the null space of the projection is always the y perpendicular, and the annihilator is a closed vector space. So these are the elementary properties of annihilator. We will discuss further in the next video.